Today I'm going to present the project about hierarchical object detection with deep reinforcement learning. First, I'm going to make a brief introduction about the problem, then about the related work related to reinforcement learning and also object detection. Then I'm going to introduce the model that we have worked with, and after that, the experiments and the conclusions. So first of all, the introduction. Our goal is to solve the task of object detection, which tries to place a bounding box around objects in images. Then what we want to do is from an initial image, the whole image, start doing some zooms in the image until finding the object. So for instance, here, if we want to find this circle, we would first have the whole image, then we would zoom in the region that we think that it's of interest of the object, of the region where we think the object is, and then we do some zooms until we finally say, okay, this is my object. So just analyzing a few regions, we would have the object detection. As you can imagine, there's a lot of possible zooms you can do in order to find this object. So for this reason, we decided to add a hierarchical partition, a hierarchy of regions that discretizes the possible movements that you can do in the image. So now, instead of doing any possible zoom, you can just, from the whole image, go to either one of these 4 quarters or go to the central region. So by the hierarchical partition, we define the possibilities that we have. So in this case, we would go to this quarter, that is the one that has the object. Then we would place again this hierarchy of regions on top of the image of the region, and we select this quarter, that is the one that has the object. And finally, we say the search is done. This is where I have my object. So how can we train it so we find objects? We are going to do it training a deep reinforcement learning agent that we will explain now what it is. So first of all, what's reinforcement learning? Here I had a citation of Kelvin, Littman, and Moore that says that reinforcement learning is a way of programming agents by reward and punishment without needing to specify how the task is to be achieved. So first, you have to think that reinforcement learning is a manner to solve a decision-making process. So in the example I was explaining, we need to train some intelligent entity that is able to take decisions. For instance, in the first image, we have to decide, okay, which is the region that I want to zoom to. So this is what reinforcement learning solves, tasks that are based on decisions. Also, it's important to notice that to train this kind of intelligent entities, you don't tell them exactly what they have to do. You don't tell them the correct answer. You only give him some reward or punishment, telling if the decision was good or bad. So this is a main difference compared to supervised learning. So here we have this figure that says, okay, this is the world of machine learning, and we have supervised learning and reinforcement learning, that it's a completely new dimension that is not supervised learning because you're not telling exactly you're not telling the correct answer, but it's neither unsupervised learning because you have some information, you have some feedback about what's going on and if the decisions are good or bad. So the main characteristics are, first of all, that there's no supervisor. We are not telling, okay, you have this image and you have to take this decision. That's not how it works. You only tell some reward signal once this intelligent agent has made a decision. It makes a decision to go to one region, and you tell, okay, that was good or that was bad. And that's the first characteristic. Also, that this reward signal, that can also be called feedback, is delayed. It's not instantaneous. We don't know from the beginning if the action we are going to perform is the good one or not. First, the agent has to do it, and then it knows if it was good or not. And this is the base of reinforcement learning. And then also that the time really matters. When you, for instance, train the agent and consider taking a decision in the first image, it already considers the following steps until the finish searches. So it's trained in a manner that it's sequential, that it considers the whole episode. Reinforcement learning is used for training games. For instance, here it's clear that you have an episode of a game. It starts and it ends. Here it's like the same. We are trying to make like a game. We start with the image and we obtain the object. And this is like an episode that is, the training considers the whole sequence. Okay, then we have defined that reinforcement learning is a way to model decision-making processes, and actually, how does it learn? How do this intelligent agent learn to take decisions? Well, it learns from experiences, just like we humans do. This intelligent agent decides, for instance, going to some region, and then from the experience it has, from the reward it receives, it learns what to do when this situation is repeated in the future, for instance. So in order to define this decision-making process, we do it with a Markov decision process that can be defined with these variables. Okay, we are going to think first in example of a human. For instance, if I want to buy one book in a bookshop, that's a decision I have to make. Which is the book that I buy? Okay, in this case, the world would be all the possible books that are in the world and everything that I can buy. But of course, when I take the decision of what book to buy, I only perceive some of the information of the world. I don't know everything. Maybe I just know some of the books that are at the bookshop close to my house, and I can read the titles in the covers, etc. That's the information that I perceive, and this is the state. And this is the information from which I base my decision, and my decision can be, okay, I buy a certain book, and this is the action. And once I buy the book, I go home, I read it, okay, and if I like it, this is like the feedback. You see that it's a posteriori feedback. First I need to make the decision, and then I see if I like it or not, and this is the reward. So, thinking about how a machine would do this process, DeepMind from Google were able to train an agent that could play any Atari game by just looking at the screen pixels of a game. So, in this case, we are going to define how will the different variables of a Markov decision process be in this case. So, for instance, the world would be the machine. All the machine that defines the whole game. Of course, you don't know everything about the game. You just perceive something that, in this case, is the screen of the game, the pixels of the screen. And then the decision, this intelligent agent, that could be a machine, decides which action to do, to move to the left, right, or whatever does in the game. And finally, here, the reward is very intuitive. It's just the score of the game. So by defining this formulation, you can train an agent to get the maximum reward when playing. So that's the basic idea. So the contributions that we have made in our work is that do a hierarchical object detection pipeline using deep reinforcement learning agents. Also, we have defined two different hierarchies of regions that we will comment later. We have also compared different strategies to describe the regions from which I base my decisions. And finally, that the goal is mainly to just analyzing a few regions in order to find an object. So the related work. Well, about deep reinforcement learning, I have already commented that DeepMind were able to train an agent that could play any Atari game, and this was a great achievement. And some months later, they were able to train a machine that they called AlphaGo machine that played the Go game. That is a really difficult game that has a lot of movements, and it requires a lot of strategy, and there's not many people that know how to play this game. And they achieved to train a machine that had even superhuman performance because it won the world champion in this game. So these were great achievements, and mainly reinforcement learning is applied to tasks like games, and also it's being applied in other fields. So now I'm going to try to summarize object detection in just one slide, which is difficult. But this is the task that we want to solve, to detect objects. So I have made here like a chronology of the different stages of object detection. First of all, the first traditional algorithms were based on low-level features to calculate some object proposals in images that consisted in locations in the image that would probably have an object in there. Then deep CNNs appeared, and we started describing these object proposals using convolutional neural networks. What happened is that we had to describe a lot of locations, passing each of them through the whole network, and this was really computationally intensive. And for this reason, approaches like faster CNN appeared, where instead of calculating features for each region independently, features were extracted just once for the whole image, and then features were like cropped from the feature map for each of the locations. Until here, these object proposals, the first hypothesis of objects, were calculated based on low-level features. But then these kind of proposals were calculated also using CNNs, but in a different manner. Instead of relying on so many regions as in object proposals, the newest approaches are based on some reference boxes, and then they are able to reshape them until fitting the object. And that's one way to not having to analyze so many regions. In fact, faster CNN, what it does is, first, it uses CNNs to extract like these object proposals from reference boxes, and it shares these convolutions to the detector also. So it's really efficient in this sense, and it's the state of the art in terms of accuracy. But then the new era are these single-shot detectors that consist on a single neural network. They don't require two stages, one for object proposals and the other for detection, and this is much faster, but also rely on these reference boxes, and the accuracy is directly proportional to how many of these reference boxes you use. So we can clusterize the different stages by saying, okay, first, the algorithms relied on a large number of locations, and in the second part, they rely on a number of reference boxes that, okay, you don't need as many as object locations, but you also need a lot if you want good accuracy. So you can imagine that these approaches, they all rely on looking in a lot of places in the image to find objects. But there's another option that is the one that we're exploring that consists on, okay, we have the initial image, and we start reshaping it until fitting the object. And this is like the refinement of a bounding box. And there are some works about this in the literature. For instance, here we have attention net, which does exactly this. You have the whole image, and it starts modifying the coordinates of the bounding box until fitting the object. This is trained in a supervised manner, casting this problem as a classification problem. So at each time steps, you have as many classes as movements you want to do to the bounding box, and you move the bounding box, then you repeat, etc. But each movement of this bounding box is independent. So you see that here, reinforcement learning could be useful because it's trained in a sequential manner that already considers where you will arrive. So this would be a good option. Here, there's this paper about active object localization with deep reinforcement learning that it's really similar to our approach. And what it does is it starts from the whole image, and it starts reshaping it until fitting the object. The main difference to our approach is that we use a hierarchical partition, so each of our actions implies a reduction in scale. And in this case, they had as many actions as every action was related to tuning one single parameter. For instance, the scale, the aspect ratio, moving to the left, to the right. So actually, it achieved its sequence of more fine refinement. but you need more steps to achieve one object. So, well, now I'm going to explain the model that we use, the hierarchical object detection model. So first, we are going to define our Markov decision process that we already told that it's the state, the reward, and the action. So first of all, the state. The state is the information from which the agent will base its decisions. So we need to provide the required information to know where an object might be. So first of all, we need the visual description of the current observed region. And also, as it is a sequential process, we can add a history vector that indicates which are the past actions performed until that moment. And then the state is the concatenation of these two vectors. Now I'm going to describe the different actions. There are two different kinds of actions. One I have already introduced, that are the movement actions. It means that the agent decides every time to which of the subregion it moves, and each of these movements are related to one action. So we have 5 possible regions if we consider the hierarchy of regions that I have talked before. Previously. And then we have the terminal action that it indicates that the search has finished. It's when the agent says, okay, this is the object, and I don't change of the current observed region. So to understand it better, here you can see the 2 hierarchy of regions we have worked with. First, we are going to think about the first one. This one, you see that we have defined 5 different sub-windows from an initial image that are the 4 quarters and a central region. And this is the movements that the agent can do in this hierarchy of regions. And then we have this trigger that it's the terminal action, that it means it's not of the hierarchy, but it says, okay, I finished my search, so this is my object. And these are the possibilities that you have once you are in this region. Then, for instance, you decide this one. You have, again, the 6 possible actions and so on. We saw that using this kind of partition, the steps were too big. With a few steps, the scale reduction was huge, and the space of possible boxes was really small. So we decided to make a hierarchy of regions that was more overlap. So here it's the same intuition, just the 4 quarters and a central region, but with a not so big reduction of scale. So now in this second hierarchy of regions, to reach the same scale, you have to perform more steps, but also you have more possible bounding boxes that could fit an object. So this is the trade-off we considered, and when we did experiments, we saw that the second option was better, and it's the one we worked with. So now I'm going to define the reward, that is this feedback signal that completely defines the Markov decision process. And as we have two kinds of actions, we also have 2 kinds of reward. The first is the reward for movement actions. This reward is related to how good it is when you move to another region. And it's related, if you are in a region and you move to another region that doesn't have the object anymore, for instance, of course, you will have a negative reward. And if you move to a region that has your object and you are removing some background, so you are zooming in the correct direction, then it will be a positive reward. So it's just to see if the intersection over union from the object with the background, with the ground truth, has improved. And well, this is a sign function, so it's simply -1 or +1, depending on if it was a good action or not. And then we have this terminal action that indicates that the search has finished. And in this case, we are not moving the region, so there's no sense in calculating any difference. We only want to know if the current observed region trespasses a certain threshold of intersection over union. And in fact, in object detection, to consider a correct detection, you have to trespass the 0.5 intersection over union, and that's when we decide that that's a good terminal action. And in fact, we use the eta equal 3 because we want to give more reward to finish the process instead of going on in movement actions. So until now we have defined our model, but we haven't defined how does the agent actually decide what to do, based on what. So here is when Q-learning comes. In reinforcement learning, what you want is to define a function Q that depends on the state S and the action A. You want this function, what it does is to define how good is a certain action when you are in a certain state. For this reason, it's called Q function because it's like the quality function. And what you actually want is that this function is related to the cumulative reward you will obtain when you perform a certain action A in the state S. So as we have defined the reward, we want to know the sum of all the future rewards that we will have when we take a certain decision. So in order to estimate this function, we can use what's called Q-learning that updates this function using the Bellman equation, that is the one we have here, that indicates remember that we want to define the cumulative reward when we do action A in the state S. And this is composed by first an immediate reward, that it's the reward we have defined previously. Okay, it's, for instance, for a movement action, -1 or +1 if I have moved to a correct action. As at reinforcement learning, we are interested in a sequence, in an episode. We are also interested, of course, in the future reward. Not only the reward that I will obtain now, but also the reward that I will obtain until I finish my search. And here is, then you can see that this is a recursion, that you have here a term that is the future reward. So once I'm in a state S, I perform action A, and I move to state S prima. And in this new state, there's an action that is the optimal one. And the Q function for these both variables indicate which is the maximum, the future reward. And that's, here it's this term. Also see that here there's this gamma, but it's called the discount factor, that is helpful to indicate the balance between the immediate reward and the future reward. For instance, in our problem, the future reward is really important, so we set a high gamma so that the immediate reward is as important as the future reward. So why is called actually deep reinforcement learning? Well, this is because this Q function can be estimated using a deep network. So here it's what we have. You have a certain state S, and you have a network that outputs one Q value for each of the possible actions. So it indicates if you are in this state and you do action 1, you will probably have a cumulative reward equal to Q value 1. So if you have this architecture, you can imagine how will the agent decide which action to do. You simply have to check which is the highest estimated cumulative reward, which is the action related to the highest cumulative reward, and do that action. And this is like the policy. What will the agent do? So now I'm going to explain our model. First, we have the part of features extraction and then the Q network. And first, I'm going to explain the feature extraction. As we said, the state is composed first by the visual description of the current observed region. And what we have done is to define, in the image zooms model, that is the first one that we test, to pass this region through a VGG16 until the last pooling layer, and that's our descriptor for that region. What happens is that for each region that we want to analyze, we are passing the region to the whole network. We also test another approach to be more efficient in this sense of not requiring to pass the whole, all the regions through the network, and do a similar approach to faster CNN that works like you have the initial image, you pass it through the network, and from the last feature map, you simply do crops to describe the different subregions. So just by taking feature once, you'd have the description for all the subregions. We have to do something that it's called Roy pooling, that consists on do a pooling so that your descriptor has a fixed size. Then, now we have described how to obtain this visual descriptor. We have defined that the Q network, you have to input the state, and it outputs one Q value related to each of the possible actions. Our state consists of the visual descriptor and also a history vector that we have explained that encodes in a one-shot manner the past actions performed. And we introduce this whole state into the Q network that consists on simply two fully connected layers. And then you have the output that are sys values, one related to each of the 6 possible actions that has our problem. So now I'm going to explain some things that are always done in reinforcement learning in order to train it. First of all, there's this exploration-exploitation dilemma that it says, okay, we have said that in reinforcement learning, first you let the agent do an action, and afterwards you tell him that was good or that was bad. Okay, but which action to select? Are we always going to select the best action with the already learned Q function or not? The answer is that with a certain probability, epsilon probability, we will perform a completely random action and learn from that experience. And from probability 1 minus epsilon, we will perform that action that it's already the one that seems better with the already learned function. And why do we do that? In reinforcement learning, they always explain the same example, that it says, for instance, imagine that you want to go to a restaurant, and you can do two things. One is going to the restaurant that you go every week, that you already know that you like it, and that would be exploitation. You go to a place that you already know that it's good. But why not trying a new restaurant that you have never tried? Maybe if you go there, you'll see that you like it more, and you will find a better solution. So that's what exploration solves. And this is the answer to not getting stuck into local minima. You always do some exploration. Of course, as you are training, every time you are relying more on the already learned policy, but you always have some random actions in order to increase to continue learning. Well, also, as what we have seen with the Bellman equation, we learn from experiences that consist of a state, an action, I obtain a reward, and I arrive to a new state. And this is like what's called an experience. When we are, for instance, looking for an object in our pipeline, we have various of these experiences, and all of them are really correlated because actually we are dealing with the same image. So this could lead to not learn properly the correlation among these samples. So in reinforcement learning, there's this concept of experience replay, that it's a buffer where you store all these experiences, and in order to train, you simply do a random mini batch in this buffer, and that's what you use for training. It's the same concept as with supervised learning. When you train a batch, you want it to be uncorrelated to learn better. It's the same. Well, finally, I'm going to talk about experiments. Here first, we have some visualizations using the image sums model, that is the one that extracts features for each region, and also using the overlapped hierarchy of regions that doesn't reduce so much the scale when performing a step. We see that the agent, with just a few steps, it can approximate to the object when there are small objects or big objects. And in fact, in some cases, by just analyzing 2 regions, it can already find an object if it's big, of course. What we can see of these results, well, first of all, is that we checked the results with image zooms model and the other presented, but the other didn't work that well, so we decided to do more experiments with this one. And also we checked that although our algorithm approximated to the object, the final bounding box was actually not accurate enough in terms that it doesn't fit exactly the object. Because it's really limited by our hierarchy. Our hierarchy of regions just lets us to have a discretized number of solutions. So there's no, for instance, in this line, there's no better bounding box than this. But in this case, we have too much background and we are cutting some part of the plane. So the hierarchy is really helpful to have a discretized number of solutions, but then it's, in terms of accuracy of intersection over union of the final bounding box, it limits us. And we wanted to check why. So here, there are some precision recall curves. In the first plot, you can see the baselines and the upper bounds for the two the hierarchy of regions test. The one that it's just the 4 quarters and the central region, and the other one that it's more overlapped. If we see the upper bound, we see that the maximum recall we can get, for instance, with the overlapped hierarchy of regions, that is the one that has more possible solutions, is really limited. It doesn't get to 0.5 of recall. And this is because what we have said, that if our agent did the best possible, the maximum he could get is not even 0.5 of recall. And that's because of the limitation of the hierarchy. So knowing this limitation and upper bound, we could test, for instance, which of the 2 models worked better, the image zooms or the one that made rod pooling. And we saw that the image zooms model worked better because we argue that when we are describing a really small region, maybe we don't have enough resolution on the feature maps, and that object is not well described. And for this reason, of course, the first method that extracts features for each subregion will work better. And the fact is that we also made an experiment of how many steps did our agent perform to find an object. Well, we did this histogram, and we checked that in the main, there were a lot of objects that were found with a single step. It meant that it considered the whole image as the bounding box, and then with 2 or 3 steps. So actually, we are performing really few steps, so we can afford extracting features for each one of the regions, and that's why we used the first model. So finally, some conclusions. Well, the conclusions are the ones that I have already explained, that the image zooms model works better. It achieves to approximate almost always to the object, to zoom in the proper direction. The problem is that maybe the final detection is not accurate enough because of the partition. And for this reason, we thought that adding another stage at the end that regresses this last region until fitting better the object could be a good solution to improve the recall of our pipeline. And well, finally here the acknowledgements to the technical support and financial support. And that's all. If you have any question.